Good evening, ladies and gentlemen, and welcome to the SAIEE Lightning Chapters webinar, where we'll be discussing tonight lightning evidence, the empirical data. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the Lightning Chapter playlist. You will find in the chat box, there's a link to subscribe to this channel. It is for free. A certificate of attendance will be issued a few weeks after this webinar once we have received the CPD validation number from EXA. I'd like to now use this opportunity to introduce you to your host for this evening, Dr. Andreas Pital, who is the chairman of the SAIEE Lightning Chapter. Andreas was born in Johannesburg and graduated with BSc Eng, MSc Eng, and PhD degrees in electrical engineering from Wits University. He is employed at Eskom and was previously employed at CBI Electric, low voltage. His technical interests include electrical distribution, insulation, and safety, as well as lightning and surge protection. Dr. Pital is a registered professional electrical engineer in South Africa, a chartered engineer in the UK, and a fellow of the SAIEE. Over to you, Andreas.
Thank you, Minx, and good evening, everyone, and welcome to our last webinar for the year. I think the first one since we had the successful launch earlier in the year. And it's a very interesting and topical program that has been set up for this evening. You can see the agenda in front of you there. The first and the last presenter will be Richard Everett. He will start by talking about quantifying the lightning risk. We will then pass on to Rydal Jardine from the South African Weather Service, who will talk about the South African Lightning Detection Network, its design, commissioning, and operations. The next speaker is then Rydal's colleague, Morne Geben, who will discuss the technology choices and application of the Lightning Detection Network. We then go on to Dr. Hugh Hunt from Wits University, who will take us through the validation parameters and results of the lightning location system. And finally, Richard Everett will conclude. I would just, before we start, like to thank the four presenters, especially Mr. Everett, who has spent a lot of time organizing it and putting things together and making sure that everything runs one to the next and everything talks to everything else, and that we have a coherent webinar this evening. Right, so I don't think there's much more that needs to be done now. Can we please then introduce Mr. Everett? Right, so Richard Everett is the National Director of the Earthing and Lightning Protection Association of South Africa. He is a member of the SAIEE and is also an office bearer of the Lightning Chapter. He has a bachelor's degree in electronic engineering, a master's in electrical engineering, and is currently registered for his PhD dealing with lightning risk. Richard has experienced and addressed a wide range of challenges over more than 30 years in the power, utility, and lightning protection industries. These challenges were overcome by collectively engaging with skilled leadership to implement sustainable lightning resilient solutions. Richard, welcome and thank you again, and over to you.
Thank you, Andreas. Oh. Is my slide up?
Yes.
Oh, cool. Okay. Righty, so we tight on time, so let me get straight in. Lightning evidence, the empirical data. So lightning is a threat to people, properties. Oh yes, let me feel that guy. So lightning is a threat to people, property, and assets, and must be contained by managing the risk. Now, ISO SANS 31000 on risk management classifies as the user of this risk management it's used by people who create and protect value. So it's important we kind of understand that as we talk about risk management in the context of lightning risk, is people who create and protect value. ISO SANS 31000 kind of revolves around these principles, framework, and processes in this illustration on the right-hand side. Essentially, in the risk management, we need to identify the source of risk, and with lightning, obviously, the key element is lightning itself, lightning data, lightning events. Gathering empirical data, I've marked the concept with a yellow circle with an asterisk. And in the principles in the ISO SANS 31000, around the concepts or principles of value creation and protection, structured and comprehensive solutions is really where we are capable of serving all our stakeholders. Inclusive should go without saying. All stakeholders need to be on board. Best available information, you'll see I'm going to talk about what tools were used in 1933 and the information that we had then, going on to the 1960s, 70s, and 80s, and now in 2021, what information we have. The emphasis being on best available. We also have to take into consideration our human and cultural factors that have an enormous impact on our ability to advance lightning awareness and lightning safety in order to achieve. So what also I think is often overlooked is that there needs to be an understanding of continual improvement. The standardization processes as well as the IEC is all about continual improvement. Standards need to be revised at least every 5 years so that we are assured of improving and literally following this process. So in the gathering of empirical data, the emphasis is before we implement a risk treatment, as per the processes on the block on the far right hand side, while we're implementing our solutions, our strategies, as well as after. So in effect, the information that we're gathering sheds light on our designs, our implementation, and then as it's implemented and working, our ability to evaluate what we have, and then our ability to take what we've got and improve it. Lightning is unless you're in Bellville in Cape Town, lightning is a common phenomena. Yesterday or last night, a friend in our community here in Salt Rock, KwaZulu-Natal, took in significances with an iPhone 12. How technologies has moved ahead. I'm going to play a video, appreciating that some of you may struggle with the bandwidth, so I've got a follow-up slide that will take us through the segments. This was last night. Multiple strokes and some very interesting patterns. Dr. Hunt will have a much more advanced demonstration, but what we're seeing is about 15 seconds, multiple strokes to ground, continuing currents, and then this interesting development of the lightning stroke going up back into the cloud. What I've done is broken this down into 15 frames. In the first frame, we see the lightning, the first stroke, treeing effect going towards ground. In the second frame, you see 2 possible points at which the stroke could be terminating in ground. Third frame is the actual contact with ground, with the charge being transferred to ground, immense heat, enormous amount of light being emanated from the channel. Frame 4 is the subsequent activity after the first return stroke. Frame 5 is kind of pulling back up into the cloud. Frame 6 is now driving a second subsequent return stroke process, or second process towards ground. In frame 7, what you see is a second path that has almost reached the ground, as and aligned with the very first stroke that occurred. So in frame 8, you can see the path of the right-hand stroke has terminated to ground. Frame 9, similar to frame 4, is the aftermath. And then in frame 10, see a little leader starting to start out from the side of the main channel. Frame 11, that frame 10 leader has disappeared. Frame 11, another one starts. We move into frame 12, where we see a similar secondary leader starting up. And then for some obscure, we know it's not obscure, but it looks really obscure. We go into frame 13, where we now start having treeing going upwards. Frame 14, the lightning current in this cloud-to-cloud discharge or intercloud discharge is starting to push up, while we've got a horizontal intercloud event. And in frame 15, we got this now charge ending up going back into the cloud. Somewhat bizarre, but the significance is that we've got the technology to even capture this kind of information on an iPhone 12. As I mentioned, Dr. Hunt will be sharing some awesome imaging as in what's coming out of the Johannesburg Lightning Research Laboratory, much more advanced than this, but understanding in 2021 we have the capability with some good selections on your camera to get this. And then pause a moment to think back in 1933. Dr. Basil Sldn, Collins and Malan trying to figure out what's happening with lightning activity and using the Boys camera, named after Sir Charles Vernon Boys, that developed this camera. Dr. Hunt is in the privileged position of actually having secured one of the original cameras. But what is significant in where we are at in South Africa right now is that way back in the 1930s, this work was being driven with the support of the South African Institute of Electrical Engineers, with a lightning investigations committee making these cameras available to the research work being done. And so it's heartening, warming that as a country we have restarted that ability by publicly launching the SAIEE Lightning Chapter in April this year. So what does the Boys camera deliver? It's this time-phased map where, when you look at the details here, when you look at the details, you can see the same activity, the branching, treeing. I'm just going to read it straight off this image: trunking, the x-axis on this particular camera in microseconds. And this really was the start of formally quantifying lightning parameters. Lightning parameters, as we know now, that we try and understand to be able to quantify adequate risk mitigation measures. So we've got that ability to visualize, but what about quantifying all the lightning activity in South Africa? So Dr. Malan, then bringing in Dr. Ralph Anderson and Dr. Andy Erickson, promoted the change of measuring lightning activity from thunderstorm days to the lightning ground flash density value, flashes per square kilometer per year. This then led to the development of the advanced flash counters with Seagrave from 1950 to 1978. And the work in South Africa with Dr. Anderson and Erickson led to the development of the RSA-10 Seagrave 10 kilohertz flash counter that came out of the CSIR, that Dr. Malan had a significant contribution to in the initial phases. Dr. Anderson then implemented a national program with these flash counters across South Africa. That the image that you see there, that's the RSA-10 flash counter, and making use of government agencies and private industry. Over 400 counters were deployed around the country. The map on the right-hand side shows 353 up to June 1981. Now, out of this information, Dr. Geldenhuys and Dr. Andy Erickson and Dr. Henry Geldenhuys produced the first national lightning ground flash density map of South Africa, which spanned the period of 1975 to 1986, 11 years. Mr. Geiben is going to be giving you updated information of the 5 sample areas that I've put on the screen there for Johannesburg 7.5, Giant's Castle, which is the Drakensberg Mountains of 13, Piet Retief of 11.7, and then on the other end, just to take two samples that are low, Port Elizabeth 0.9 and Eastland 1.6. It's notable that this map shows that the Drakensberg Mountains range, Lesotho, has a higher flash density than Piet Retief. When we look at Mr. Gaben's results, you can see an interesting change there. So we've got visuals, we've got electric field measurements, wide areas. The SAIEE Study Committee 33, which focused with Working Group 33.01 on lightning, resolved that it was best measured directly. So with the two towers that in the initial phases of developing lightning characteristics was in Switzerland with Dr. Berger, and over time Dr. Anderson and Dr. Eriksson joined them, and so that was the one tower. The other tower was in South Africa with Dr. Eriksson and Dr. Henry Geldenhuys. And the lighting parameters from these two sites, predominantly from the site in Switzerland, made up the lighting parameters as documented in the Electra 69 in 1980. Just wanted to point of note, I'm very much a fan of South Africans, so all the non-South Africans, please humor me while I very proudly keep on talking about South Africans contributing to our scientific body of knowledge. Dr. Anderson was convener of the Working Group 3301 for 14 years from 1970 to 1984, and Dr. Eriksson was a convener of the Working Group 3301, as well as he chaired the Study Committee 33 for quite some time. I'm not going to go through all of these, but just to be aware that from 1980 through to 2013, there have been numerous SAIEE technical bulletins covering a range of from the lighting parameters to the lighting location systems to power lighting data, lighting information for power system performance. And I just want to draw your attention to the Electra 69 in 1980, and then a revision of that 33 years later with the Technical Bulletin 549, convener Dr. Vladimir Rakov, lighting parameters for engineering application. So there's a lot of work that we are part of. As far as the lighting location systems are concerned, covering what we're covering today, Dr. Bill Chisholm was convener of the Technical Bulletin 94, Technical Bulletin 94 in 1995, which covered the technologies that are available for lighting location systems, lighting detection and reporting. More recently, in 2009, SAIEE Technical Bulletin 376 for the Working Group C4.404. So Study Committee 33 became Study Committee C4. Dr. Gerard Diendorfer led that. And the particular emphasis here is that the cloud-to-ground lighting parameters can vary depending on the performance of the lighting location system. It's very important to appreciate that, and the findings from that technical bulletin is excellent. Okay, so talking about the standard IEC 62858, lighting density based on lighting location systems, the foundation by which we would measure the performance. The new project, essentially two important parts. New project, when I say new project, is a new project in the standards IEC. International standards for lighting protection provides methods for evaluation of the lighting risk on buildings and structures. So these are the standards. However, the lighting flash density, NG, or the ground flash density, GFD, is the primary input parameter to perform such an evaluation. So it's important to understand that the core of the process of doing quantifying lighting risk is the lighting flash density. So just before I hand over, the purpose of the standard is to promote harmonization of the national specifications to give common ground flash density values so that the risk valuation would be harmonized, not only as a procedure, but also for the results. So the purpose would be to specify the requirements and tests to be performed independently of the technology used, and it's relevant to two parts: the performance of the hardware as well as the data processing. So the performance of the hardware would be detection efficiency and the location accuracy and the quality of the measured data, whereas the data processing would be the sample data, etc. And with that, I'll hand over Minx to Rydal Jardine.
Okay, so Rydal is the manager of infrastructure asset management at the South African Weather Service. He holds a B.Tech degree in electrical engineering from the Tshwane University of Technology. He has over 23 years of experience within the South African Weather Service, working with radar, HF transmitters, lightning detection technology, upper air sounding systems, manual and automated weather observing systems. He is also currently overseeing the operations of the Southern African Lightning Detection Network. He is also a member of the chapter and one of the office bearers. Over to you, Rydal. Thank you and welcome.
Thank you, Andreas. So on my presentation, basically what I'm going to be trying to take the team through is just the background to the South African Weather Service network, the area that it currently covers, the legislation and compliance that it needs to comply with, the scientific and engineering principles that is applied to the technology we use, some basic indication of the lightning data applications, which will be broadened out later in this presentations, and then of course just a basic cost recovery principle.
Sorry, Rydal, waiting to view your screen.
Sorry?
We're waiting to view your screen.
Oh, I thought it's available. Okay, sorry about that. Can you see it?
Just swap your display settings, please.
Okay.
At the top of your screen on the left-hand side, in the middle is display settings. Click on that. Swap swap that.
Okay.
Yes.
Sorry.
Perfect.
Okay.
Thank you.
No problem. Sorry. So let me go through then. So the background, basically, the South African Weather Service started their network around 2005 through an engagement with the local South African Eskom power generating agency. This network primarily consists of cloud to ground lightning detection network, but it does detect about 30% inter-cloud lightning activity as well. The network currently consists of 24 sensors that is owned by the South African Weather Service and one by its neighboring Eswatini Meteorological Services. 16 of those sensors currently is of the LS7000 version together with the Eswatini system. 4 of those systems has also been already upgraded to 7001 and another 4 has recently been upgraded to the 7002 version. And the total lightning process has also recently been upgraded. And of course, there's continuous development where we are having a 3-year rollout plan where we intend to upgrade the entire network as well. Thank you. That being said, the network area coverage is then as follows. As you can see on the left-hand side, this is where our current sensors are located. And then the right-hand side, I've basically given you a layout of the gridded map, which gives an indication of the location accuracies and the detection efficiencies per gridded block. And as you can see, there's still some areas around the outskirts of the network where we need to improve on. But we have, at this point in time, got a map where the detection efficiency is above 90% and the location accuracy is within half a kilometer or 500 meters. The South African Weather Service also then has a South African Weather Service Act, which is the Act 8 of 2001, which needs to comply with the provision of severe weather warnings over the South African environment. And this is linked to the thunderstorm warning system, as well as linked then to the SUNS 62793, which is the protection against lightning. From the IEC 62858, we also have certain ways of validating the performance of our lightning detection network or our lightning location system. And those 4 criteria are then the network self-referencing, the rocket triggered lightning and pole structure studies, video studies, and intercomparison. Amongst these, the South African Weather Service has already obtained some clearances on that. There is a test that has also recently been done with the Johannesburg Lightning Research Laboratory at Wits University, where 2 of those criteria has already been met. This was involved with the Telkom and the Centec towers. And of course, the outcome to that result was the achievement of a medium location accuracy of 68.5. But Dr. Johan will later explain further on this exercise they've done. There is also, according to the same IEC criteria, we need to ensure that at least we perform above 80%. As I've indicated, we are currently at 90%, and that we have to stay within approximately 500 meters, of which we are currently meeting that as well. The minimum observation period of normally 10 years, we have already exceeded that, since we've had our system up and collecting data since about 2006. So we have been able to actually put together a new GFD. So the ground flash lightning data system is there, and we will be able to explain further on that when the other presenters present. On the side of our maintenance activities, just for clarity, these are the activities that we do currently to ensure the performance of our network is up to standard. We do preventative and predictive maintenance activities. We have corrective maintenance activities, and then of course the network calibration and improvement, modernization and upgrades. Currently, the system that we are using does both time of arrival as well as magnetic declination as part of its principle of detecting the lightning discharge. For the accurate lightning detection and efficiency and location accuracy, our network has currently been set up to work with a minimum of about 4 sensors within an area where we can cross-compare to ensure that there's a quality of our data. Our preventative and predictive maintenance is performed on quarterly basis activities. The monthly or the daily monitoring of the networks ensure that we are able to actually speedily assist and to get the system up and running soonest. At the same time, we have the deployment of regional personnel that has been trained also by the original equipment manufacturer to ensure that there is compliance to the requirements, as well as we are an ISO accredited organization as the South African Weather Service. With the close monitoring of our network, we are able to actually operate and follow the trends in the technology development and ensure that we modernize and upgrade our network as speedily as possible. There's an annual network calibration process currently in place, and this is performed by an external or a third party to the South African Weather Service. From basic principle of understanding the detection of the lightning activity, the propagation of low frequency electromagnetic waves. There is the first wave, which is the ground wave that is represented here by the G indication. And then of course you've got the 3 sky wave that is just reflecting back. The most important here is to remember that the time of day and the number of sky waves and the intervals between the successive sky waves reads the observer at an indicator of distance of the stroke, as well as the strength of the stroke itself. Then there's the radiation field pulses signature that is being created by the discharge of the lightning discharge, which is in the frequencies of the very low frequency ranges and the low frequency range. Explaining it was a little bit the magnetic direction finding principle. This is a principle where we make use of the magnetic antennae, which is erected on a flat electric antenna, enabled to detect the polarity and the electromagnetic field strength. These are configured then to unique the cloud to ground lightning discharges. Incoming electromagnetic strokes are then returned, and as can be explained at the bottom there by the graphic representation, the three sensors then enables you to be able to pinpoint more specifically the location of lightning activity. Then the time of arrival principle. The time of arrival principle is two principles that is being applied here. Firstly is the hyperbolic principle and then the circular principle. But with the hyperbolic principle, as you can see at the bottom right-hand side, there could be potential false representation, and therefore the circular application is also introduced to get a much more accurate result. That being said, it then indicates the greater advantage of using both the magnetic direction finding and the time of arrival technology principle, where you can then actually reduce your network. Even if you want to just use two sensors, it would be able to detect it much more effectively. However, it must be stated that even though we use these combined principles, it is not yet providing us with 100% accuracy on this detection. However, you can use it to calculate the degree of accuracy. This is just some principles that we can apply from the side of how we can optimize the network's performance or the data available from the network, where that if you should have a situation where you have a radar system being down, you could actually use the lightning detection network also to then track the storm formation and movement. Where, for example, if you look at the right-hand side picture, it represents 3 frames there. There's a red circled area, there's blue circled area, and a green circled area. Those areas are indicating the current movement of the storm, where red represents where the storm is currently. The blue is where the storm would be moving towards in the next 30 minutes. And then, of course, within the next 60 minutes or an hour, where the storm would be at that point in time. Here's just examples of some comparison between the lightning detection actual data and what comes from a forecasting model for the storm formations and tracking. And as you can see, there's very close collaboration between them. The same happens on the day 2. We have just done it to show exactly that there is still that correlation between the two screens as well. Your lightning data can also be used for climatological perspective in the sense of lightning flash density, where you can have your medium peak, you can have your average flash multiplicity, and you can have lightning ground flash density. There's also a risk mapping principle that you can apply from a climatological perspective. And then, of course, I'm just indicating that the South African Weather Service is currently providing the services to the power generator Eskom to help them with the overhead design and, of course, the performance of the network, tracking of faults through fault correlation. And then there's the aviation industry, where they use this information for circular format of at least 15 kilometers away from the airport, and then broken down into 5-kilometer radius circle rings to enable them to be able to perform the operations more effectively. And then, of course, the information, it can also be used for insurance purposes. This is just a representativity of exactly what I've just said now, where the insurance industry is mapping exactly the amount of activities that is happening that links to the amount of requests from the insurance industry. The aviation industry, as I've indicated, the 15 radius rings around the airport, in the case of our Tambo, for example. And then, of course, the Eskom power line tracing the faults and resulting in more effective network supply. Thank you. Thank you.
Thank you, Rydal. Before we move on to the next presenter, can I just remind you, please, that if you have any questions, please put them into the question box. Please just indicate who they are for, which of the 4 presenters your question is for, and then we will cover the questions at the end. So if you have anything you'd like to know something more about, or have a comment or experience to share, please put those into the question box. Okay, our next presenter has something in common with me. We both have surnames that many people do not pronounce correctly, and I will probably not pronounce Mone's surname correctly either, but I'll give it my best shot. Mone Geben is a lead scientist in remote sensing research at the South African Weather Service. Sorry, the thing has just changed. He oversees all research activities related to remote sensing, including lightning radar and satellite research. He holds a master's degree from the University of Pretoria, which focuses on developing a model-based lightning prediction system. He has worked in the field of lightning research since 2010 and includes, amongst others, research into the Southern African Lightning Detection Network. Mr. Geben is currently enrolled for his PhD degree at the University of Pretoria, and he focuses on improving thunderstorm nowcasting using artificial intelligence or machine learning with input from radar, lightning, and satellite information. Thank you, Mone, and over to you.
Thank you very much, Andreas. Let me just share my screen. I hope everybody can see it. So I'm going to just talk about the technology choices that we made at the South African Weather Service, as well as some applications that we also make use of for clients at the Weather Service. So just to start off with a bit of background. So myself, I'm the lead scientist for remote sensing research at the South African Weather Service. And our specific group falls within the research and development section. So in our research group, we do fundamental as well as application research, and we focus on various different topics ranging from observation research, weather research, all the way to market intelligence research. So as a weather service, we of course have to provide the public with weather forecasts, and this ranges from all the way from nowcasting, that is your first 0 to 2 hour forecast scale, all the way up to climate change. So of course we produce various scientific output, we develop products and applications, firstly for our forecasters that needs to provide the warnings to the public as well as clients. And then of course we also support these clients with customized products that we develop for them. And this is of course all to fulfill the SAIEE's mandate. So in our specific remote sensing group, we primarily focus on 3 different areas, which include lightning, radar, and satellite. So of course, today I'm going to focus on the lightning side. So as I mentioned, in order to fulfill the source mandate, we of course have to look at the entire value chain, where we basically start off with our infrastructure, our observations and data collection, and then we process the data as well as archive this data. And this then enables us to perform research as well as to produce products and services, which we can then provide to clients, which is either our internal forecasting clients or our external clients. So I'm just showing at the bottom right and side the value chain at the South African Weather Service requires close collaboration between all the different units within the Weather Service. So we are in research, and Rydal, that you just heard in his presentation, he's from the technical services side. And then of course we also have ICT, climate services, forecasting, as well as air quality and aviation weather center. So the importance of this is that we all need to work closely together. So if one of these sections fails within this value chain, then of course all of us are affected. So that's why we need close collaboration. So of course, lightning information also forms a very important component of this value chain, and therefore we require accurate lightning data for us to perform research and as well as to support all the forecasting as well as client needs. Sorry, my slides are a bit sticky. Okay, so before we can even start performing research and developing products and services and provide solutions to our clients, we of course require accurate lightning data. So what we basically need is we want flash detection efficiencies exceeding 90%. We want medium stroke location accuracies less than 500 meters. And we also want classification accuracies, that's by classifying cloud to ground and intra-cloud lightning and the difference between the two. So that's what we need in order to provide services to our clients. And of course, these criteria we extracted from the IEC 62858 standard, and that's where we got these numbers from. So in order to achieve all of these requirements, there's various things that we need to consider for our lightning detection network to be able to perform according to these standards. So the first thing we need to consider is the sensor baseline. So that's the distance between our sensors. So for example, in this example on the bottom right-hand side, you can see that the sensor baseline is 200 kilometers between sensors. Then we also need to consider the sensitivity of the sensors. So that's the vision of the peak currents that's measured by the system. We also need to consider the sensor uptime, so that the sensors are always available. And of course, we also need to consider the location method. So whether it's time of arrival, magnetic direction finding, or both. And of course, this image also gives you a good idea of how a lightning detection network works. So multiple sensors in the network participate in the detection of a lightning stroke. And this is an example of an ideal situation where you have, for example, 6 sensors with a sensor in the middle. So just to give you an indication of how we came to choose the network that we currently have at the Weather Service, we, for example, considered the sensor baseline distance between the sensors. And this was basically based on one of the Seagray reports that Richard also mentioned earlier, where they tested what the effects of sensor baseline distance and location method will be when you consider various baselines as well as adding and removing sensors into this scenario. So they considered 6 sensors, as I just showed you, with 5 on the outer skirts and then 1 in the middle, so to give you this pentagon shape. So they also considered baselines of 150, 200, and 300 kilometers, and they also looked at various different permutations, where they first included the 2 sensor required to detect the lightning solution, which is the time of arrival plus magnetic direction finding network. They also included 3 sensors where they only considered time of arrival, but with 3 sensors, then you stand the chance to get ambiguous locations, as Rydal also mentioned. And then they also included 4 sensors where the time of arrival network can then avoid the ambiguous locations. So based on these parameters, they first considered a 200 kilometer baseline between the sensors, where they considered all 6. Then they also removed the center sensor and also one of the border sensors. So by removing one of the border sensors, which is of course significant for our network on the outskirts, so between, for example, Botswana and South Africa. So that also will provide us some detail of what the effects will be on the borders of the network. And then they also considered a 150 kilometer baseline as well as a 300 kilometer baseline. So the interesting thing is when they looked at a network needing 2 sensors, which is a combined technology sensor at baseline of 200 kilometers, for example, the detection efficiency was 96.5%. And if you, for example, consider a time of arrival network at a baseline of 200 kilometers, then the detection efficiency drops to 76.6%. So there's various different scenarios. So you can see that basically the detection efficiency drops when you start removing sensors, and also if you only consider one parameter, for example, the time of arrival section of the detection. So the basic conclusion was that with a combined technology, you require fewer sensors with baselines, for example, between 200 and 300 kilometers in order to achieve a greater than 90% detection efficiency, while a time of arrival network you can also install, but then you require more sensors with baselines 150 kilometers or less. And they also, as part of this report, they looked at the Austrian lightning location system, which consists of 8 sensors that's very densely separated by about 120 kilometers. And they examined the performance changes due to not using some of the sensors from the neighboring networks that were participating in the Euclid network. So they also considered various options where they looked at the 8 sensors by looking at the time and angle information, so combined technology, by only looking at 3 sensors with the combined technology, and then only looking at the time of arrival aspect by using 3 sensors as a minimum to detect lightning, as well as 4 sensors as a minimum to detect lightning. And basically what they found was that relative to the Euclid network, as soon as you only use 8 sensors, your detection efficiency is 89% compared to Euclid. But as soon as you go down to 3 sensors with the combined technology, it drops to 61%. And then if you only use time of arrival, the detection efficiency drops even further. And then what's also significant is that the median peak currents in this system then also decreases, going to 8 sensors compared to Euclid. And what's also significant is that going into the time of arrival method, that the peak currents also drop even further. So basically what this means is with 8 sensor network using combined technology, we detect more flashes with small peak currents compared to a time of arrival network with a 4 sensor configuration, and higher peak current is required in order to exceed the detection threshold with the time of arrival system. And this, of course, you can see that there's a shift in the peak current distributions, which of course affects your things like your system designs, which is quite significant. So at the time when we installed the network, based on these type of studies, we then opted for the combined technology network. So to meet the performance requirements that we needed for the country. And this was basically based on the fact that with the combined technology, we could have baselines between the sensors of 200 to 300 kilometers in order to achieve this performance. And basically, we are now confident that our network is performing really well and meeting this criteria. And this is just to show the average number of sensors that usually participate in the detection of lightning. So with the central interior, you can see that more than 7 sensors over the interior and even up to 10 and 11 here over the Free State area. But of course, over the Western Cape and Northern Cape, as well as Limpopo, we on average use 4 sensors to detect lightning. So there is some areas of improvement that we can still look at. So of course, with this accurate data, we can now with confidence use for research as well as product and service development for clients. So then looking at some applications, of course, one of the applications is the real-time displays for forecasters, which are very important. So there are various different options available, including real-time displays as well as near real-time displays. They can overlay it on satellite images, etc. As Rydal also mentioned, we can supplement other observations like radar to get storm tracks, which is useful for thunderstorm alerts. We can also include it into other systems that we run at the weather service. So here's just an example of a satellite system where we included lightning information, and then we could start tracking thunderstorms that we missed without the lightning information that is now included. And the information is then also provided in the metadata of the storm cell. And then, of course, the statistical model that we produced with 2 years of lightning observations. So as Rydal indicated, we can then provide a forecast early on the 18th of January, for example, for 19 January, as well as on the morning of 19 January. And then if you compare it to actual observed lightning data, you can see that there's a very good agreement between the two. And then we also can make use of the lightning data as a verification tool of the performance of various products. So we can calculate various statistics to see how the actual products are performing. Then, of course, another important component is to verify lightning events. So I'm just going to use the 13 November 2021 fire that caused a fire at the total filling station at the Lower Sabi Rest Camp in Kruger National Park. So according to Eyewitness News, lightning caused this incident. And you can see that this is how the station, filling station looked like, and this is after the fire. So a quick analysis on this day showed that there was many lightning strikes that occurred in this area, and that the fire started at between 19:30 and 8 o'clock in the evening, according to media reports. So for each lightning strike, we can look at 99% confidence ellipses, where we can then say with a 99% probability that lightning occurred somewhere in this ellipse. So on this specific day, we could then look at and analyze the lightning, and basically we saw that there were 4 possible solutions. 3 of them were only detected by 2 sensors, and this is because of probably the fact that the sensors were far away from the lightning strike, and only 2 sensors caused this oblique angle. But basically you can see that we were able, with our combined technology, to even detect these lightning strikes by using only 2 sensors. But an analysis of the day, we then determined that this lightning strike that was detected by 5 sensors, which is also very close to the actual filling station, was the actual, in all likelihood, the lightning strike that caused the fire. And this is just to show you that the network detected the lightning strike 135 meters from the actual filling station. So of course we have all the historical flash density and stroke data available since 2006. So we can then, of course, use this information to create a new flash density map for South Africa. And in 2017, we produced the 11 years lightning data flash density map for a full solar cycle. And this was based on more than 240 million lightning records that we used. And this is then just to now show the new 11-year lightning ground flash density map, which is, of course, high resolution map, and it indicates the areas of South Africa that receives most lightning. So for example, this area receives most lightning. And this is just a comparison between the old CSIR map as well as the new lightning ground flash density map. And based on this, you can see that some of the values have now, of course, changed. So for example, Johannesburg has now higher flash densities, while a place like Giant's Castle has slightly lower flash density values. And this data is, of course, going to be very important for risk management in South Africa. Thank you very much.
Thank you, Morne. Those were two very interesting presentations, and I think we've had a much deeper insight into how the lightning location system of the Weather Service operates, and also its various parameters. So thank you, Morne and Rydal. Our next speaker is Dr. Hugh Hunt, another member of the SAIEE Lightning Chapter and member and office bearer. In fact, he's the vice chair of the chapter. Dr. Hunt is a senior lecturer at the School of Electrical and Information Engineering at Wits University. He's also the head of the Johannesburg Lightning Research Lab at Wits. He was born in Johannesburg and completed his PhD at Wits, looking at the use of lightning location system data in forensic investigations. He has worked with the South African Lightning Detection Network and in Brazil with the RIN-DAT system. He currently, as I said, heads the Joburg Lightning Research Lab and is vice chair of the Lightning Chapter. Hugh, we look forward to your presentation.
Thanks, Andreas. Just to confirm that you are seeing my screen there.
Yes.
Great. Okay, so I don't want to take too long. I think I'll get to the point here, but I think that's fantastic what Rydal and Morne have set up and talked about the South African Weather Service. And what I just want to show is a very small part of what we've done with some of our high-speed video studies of lightning and how that links into what the solid work they've done in getting the network operating so well. So just as a brief overview for what I'll talk about, I think there's been quite a lot of mention of performance metrics and validation and these things and the IEC 62858. I just want to briefly chat through that and just think a little bit about what do we mean by those things. A big thing for me that often comes up when thinking about lightning location system data is this really important definition we talk about when we're talking about a stroke or flash, or what is a lightning strike. And I think I'm going to want to spend a little time thinking about that just to get it right in our heads. And then lastly, I'm going to show you the evaluation of the SALDN that an MSc student of mine did 2 years ago, and some of the results that came out of that. So firstly, the main, and I think Morne and Rydal brought this up, and very important characteristics, and these are generally considered the performance metrics of a lightning detection network, lightning location system, any kind of lightning measuring or remote lightning measuring system. And of course, they are detection efficiency, location accuracy, classification, and really what we're talking about there is, are you detecting lightning that attaches to the ground, or are you detecting lightning in the clouds? And then the other one that's often used is the estimation of the peak current. So how accurately are we estimating the peak current? But the most important ones really are this detection efficiency and location accuracy. And detection efficiency, where we're really talking about there is it detecting all the lightning that happens? So you have a system that tells you lightning has happened somewhere. Is it getting everything? Or is it missing some of the lightning events that actually happen? And location accuracy, then how accurately is it actually locating that lightning event? And we're going to think carefully about the location accuracy sometimes as well, because while we might think that the more accurate it is, we just want an exact perfect pinpoint location. You know, if we think about a lightning channel, it's not actually a perfect straight line from the cloud to ground. So we've got to be careful to interpret a dot on a map as a representation of where lightning exactly attached, or is it a representation of the lightning event as a whole? These are things we have to just keep in mind and think about. So, but I'll talk through this in more detail, and then I'm not going to focus so much on the classification and current estimation today, but I'll make some mentions of talking about that later. We've brought up the IEC 2858, and I think really important to note about that document is really talking about the criteria that's necessary in order to generate a flash density map from lightning location system data. So that's where its focus is. But with that said, it's the techniques it recommends and the using these performance metrics and these the way it goes about saying how an LLS should be validated are not only relevant to flash density, they're also relevant to other things such as storm tracking, power line fault. If we're trying to see, did lightning cause a fault on a power line? The type of insurance investigations Monet talked about there. These parameters are relevant to that as well, even though this document only really worries about flash density. It's not the only thing to consider here. And then the document also talks about these different validation approaches, and these are not so obvious what they're actually getting at here and why. And I want to try and unpack these a little bit and see if, and maybe this is a good point. If I'm not being clear, please ask questions. They give these 4 different techniques. One is the network self-reference. Then there's the rocket-triggered lightning and tool object studies. Then there's video camera studies, and then intercomparison among networks. Now, really, the 2 in the middle, the rocket-triggered lightning and tool object studies, video camera studies, should really be grouped together as what we might refer to as ground truth studies. So there you're going, well, I'm actually seeing lightning. I'm seeing it in a video. I'm making a measurement on a tower or something. I have a real evidence, ground truth evidence that lightning has happened. And what did the lightning location system measure? And how did it report this lightning event that I really know did happen? That's what we're talking about in that kind of study. Intercomparison among networks is where you say, well, I've got one lightning location system and another lightning location system. They both measured a lightning event. What did they both say about that lightning event? Did they both say exactly the same thing about it? Did they both detect it? Did they both locate it in the same sort of place? How do 2 different networks compare to each other? And then the most subtle one is the network self-reference. And Rydal showed you a fantastic picture there of the map of South Africa showing where the detection efficiency of the network is best. And you can see how the detection efficiency started to fall off a little bit as you went outside the network. And that really is the result of doing a network self-reference. And this is a really important technique, particularly for running a network and making sure the network is getting a sense of the performance of the network across the entire network. But really what you're doing there is you're comparing the individual sensors in a network to each other. So if you have a lightning strike in Johannesburg, you then look at your different sensors and you go, what did each of those different sensors measure? Maybe you have one sensor that didn't measure it. And you go, okay, why didn't that sensor measure it? Maybe there's a problem with that sensor that's pulling the overall detection efficiency down, as Monet described very clearly. And so that's really what the network self-reference is about. But of course, the problem is with this one is that if there was a lightning event that none of the sensors detected for whatever reason, you're not going to pick that up by doing a network self-reference. And also similarly in the intercomparison, if both the two networks you're comparing don't pick up the lightning event, you're not going to know about it. So these are very useful tools, and they're generally easier to do, but the ground truth studies in the middle there are really important for really understanding whether the network is and how the network is behaving. Of course, these are easy. The network self-reference and comparison are easier to do across the entire network, and so really useful tools for doing that. So what I'm going to show you a video here, and what we've got is a high-speed video filmed over Johannesburg, and then we've got an electric field measurement. And I really want to answer this question: what are we talking about when we talk about a stroke, a flash, strike? And really, what I would first say is the word strike should actually, that's a very strong colloquialism. We don't talk about lightning strikes. We talk about flashes and strokes. And a flash is the overarching event. So this whole video shows you one flash. So you see the leader come down, and you can actually see where that lightning attached. But then quickly after that, we get this subsequent stroke. You can see it's following exactly the same channel and striking to exactly the same place. And just note the time there in the video is we're not even changing the second, right? So this is a very high frame rate. So what you're seeing here is a single lightning flash, but it's made up of multiple strokes. Now, the other important thing to note here is the electric field here. Andreas, I'm just getting a note that the video is not coming through. Are you seeing it?
Yes. I'm wondering if it's not a connection problem for some people.
Okay. Good. I'm glad it is coming through. So what's important about this electric field you're seeing measurement here is that's the kind of thing a lightning detection network is measuring, right? It has a sensor, an antenna, and it's seeing these spikes. Each one of those sensors of the SALDN is seeing these spikes in electric and magnetic field. So that's really how it detects lightning. So even though this is a lightning flash, an LDN or LLS actually only detects the strokes. It has to then subsequently figure out, based on the difference in time between them, that these were all part of the same flash. So if I go look at what the SALDN had to say about this flash, I'm going to play it here. So here I've got a map, and on this map in little red dots are going to appear what the SALDN data measured about this particular flash. So you can see as you get the first pulse there, you get a red dot over there. And then as we move along, we see that second stroke, and that had a location reported over there. And then we carry on, and we're going to get our next stroke that happens. So note already, even just between those two strokes, there's a bit of a difference in reported location. Next stroke, even though we can see in the video they're attaching to exactly the same spot. The algorithms and based on this triangulation method, we don't always get the locations in exactly the same place, but they are very tightly clustered together. I'm going to pull the video back a bit. I want you to notice this little pulse down at the bottom here. You'll see that wasn't actually detected. And that's because you can see from the electric field, it's too small. It was such a little pulse. It still had you can still visually see it in the camera, but it wasn't a big enough pulse for the SALDN to detect it. But it got all these other strokes. So, and there's the last one. So overall, this flash, we had 1, 2, 3, 4, 5, 6 strokes making up this flash. And these all represent that single flash to a single location. And so that really encapsulates the two things I want to focus on there is location accuracy and detection efficiency. So the detection efficiency was it got the flash. It missed one of those little strokes, but there was a very small stroke and didn't have a lot of intensity. And then the location accuracy, well, it's clustered them all very well together. This first one was a little bit out from the others, but overall, it's got a very tight cluster there, giving us a very good idea of where that flash really attached to. And so this takes me to the evaluation of the SALDN, and this was the main analysis was done by my MSc student Hayden Fensham, and really what he looked at here is a bunch of these high-speed videos that we have, comparing them with the lightning location system data from the SALDN, and trying to get a sense on measure some of those performance metrics we're talking about. So the first thing he did is look at these downward, like the one we've just looked at, downward negative lightning, right? And he had a total of 163 different videos, flashes. Of those 163, 151 detected at least one stroke in the flash. So they detected the flash. And that gave, essentially, from that you can estimate that, well, in general, the SALDN detected 92.6% of the videos filmed, which is a very good detection efficiency. The other thing he looked at is upward lightning. So the Sentech Tower in Johannesburg, and of course, as you can see in this video, upward lightning looks kind of different. And then also what starts here is a lightning event off the Telkom Tower. Now, this initial leader coming off these towers doesn't really trigger the SALDN because it doesn't have a sudden sharp pulse. But these other pulses that start happening subsequently are strong enough to detect it. So it's not uncommon for an lightning detection network not to detect lightning off a tall tower like this unless it has proper pulses. And what you can see is this is factored into the analysis here. So a total of 43 videos of upward lightning were filmed. Only 24 of them were detected. But if we split that up into the two different kinds, so ones that just had a leader like this and didn't actually have any major pulses, okay, they weren't so well detected as expected. But the ones that do have proper pulses, they were very well detected, 93%, which gives us a very good indication of how well the SALDN is behaving. The other nice thing about studying tall tower lightning, while it doesn't give us a great, doesn't always give us that lovely return stroke, is it gives us a known location. So we know exactly where that tower is. So we can then compare that with SALDN location reports and get a very good sense of the location accuracy. This just summarizes the detection efficiency there, that's downward and upward flashes. And this is the stroke detection efficiency. So how well did it detect every individual stroke? And of course, that's slightly reduced compared to the overall flash detection efficiency, because to detect a flash, you just need to detect a single stroke within that flash. But to detect every stroke requires a bit more, as we saw in that flash. But overall, still very good performance. So what you're looking at here now we want to move on to looking at location accuracy. And what we're really looking at here is where Johannesburg is. This big red circle is the Sentech Tower. This purple square over here is the Hillbrow Tower. And these blue triangles show you where SALDN reports of lightning that was filmed at the Sentech Tower, and the green diamonds are lightning that was filmed at the Hillbrow Tower. And the blue star over here is where the camera was, looking across the city like this. And so you can see, as we would expect, and very good, the SALDN reports of the Sentech Tower are clustered tightly around the tower there, clustered tightly around Hillbrow Tower there. I'll zoom in there a bit. So this is now around Sentech, this is now around Hillbrow, and you can see we're well within 200 meters clustered around the Sentech Tower, well within 200 meters clustered around the Hillbrow Tower. So in general, the overall median location accuracy was about 59.2 meters, and slightly different between the two towers, but that's neither here nor there. We often talk about location accuracy in terms of the median value. So we're saying 50% of the data was lower than that, 50% was higher. Of course, there's other statistics that describe the distribution, but the median is usually the one quoted. This is showing you the location accuracy based on the downward lightning events. This is a slightly more complicated analysis because you don't necessarily know with those downward events exactly where they struck, But because you get that little cluster of strokes, you can find the difference in distance between all the strokes within a cluster, and you can get some estimate of the location accuracy. And as you can see here, doing this on the downward events, it's slightly higher than the tall tower events. That could be due, but not much higher, still well within reasonable values for location accuracy, and goes to show how well the SALDN really is functioning. Probably the slight increase is due to the fact that tall towers, you've got these two, the Centric and Hillbrow Tower, two very tall towers there, a nice straight conductor going straight up. When that lightning current flows through the tower, it propagates very evenly. It makes it a bit easier for the SALDN to locate it. So then it's possible that it's slightly more accurate on the tall towers, but not by much, because we're seeing very good values here, even for the non-tall tower events. And then we haven't done the analysis yet, but now we have our current measurement installed on the Centric Tower as part of the Johannesburg Lightning Research Laboratory. And if I play this video here for you, which now doesn't want to behave. Unfortunately, the video is not playing, but I'll run it through. You can see we measuring lightning currents on the tower itself. This is actually the lightning current flowing through the tower. This now gives us future studies we'll be doing with the South African Weather Service, so actually to compare the peak current estimates of the SALDN and see how well it's estimating that. So in summary, the IEC 62858 gives us some very good performance metrics to evaluate and validate lightning location systems against. Just making that note, that definition of a stroke and a flash, really important to understanding LLS data. LLS data comes in strokes, and we have to group it into flashes. Really important thing to understand there. And then finally, the South African Lightning Detection Network, from our analysis, has roughly a detection efficiency over 90% and a median location accuracy within 120 meters to 50 meters. And that's a median value. And that's done through our ground truth validation. Thank you.
Thank you, Hugh. A very interesting and very visual presentation. Every time I think there's not more that you can do with this work, you come up with something else. That's fantastic. And to conclude, I'll pass back to Richard Everett.
Hey, I'm back. Sorry, just grabbing my slide. And so in summary, as we talk about the risk management, trying to come up with the most effective lightning protection solutions, there are let me just put my video off. When I switched the wrong thing off. There's some considerations that we need to look at as been presented by the information that's on the table now. The ground flash density maps of 1975 to 1986 from the CSIR presents a considerably lower, in general, ground flash density value than we see in 2006 to 2017. Now, when we look at these numbers, samples out of the areas, we see in Joburg that it was previously 7.5 and now it's 13 to 19. Giant's Castle marginally down from 13 down to 12. Piet Retief from 11.7, it's way up at 17. And Port Elizabeth and East London, not much change. Significance is when we start looking at the resolution, that when we take the old flash counter data in the CSIR's ground flash density map and compare it to what we have here. The Eastern Cape is an interesting example where there is a very high copy, and Eskom has a repeater communications repeater tower on it, and we note that the flash density on that copy is up at 15 flashes per square kilometer, which is comparable with the lightning activity in the eastern parts of Mpumalanga and northeastern parts of KwaZulu-Natal. Just to draw your attention back, if I may just go back to this slide, what we do see about the lightning activity across South Africa is that the highest lightning activity is actually in the eastern escarpment of the Mpumalanga Piet Retief area and down to Paul Petersburg, as opposed to the Drakensberg. So from that perspective, the data that we have from the CSIR is considerably skewed. The question that is often asked is, so has lightning activity increased? And when one looks at these numbers independent of the detection, one would start concluding, now look, Piet Retief has gone up from 11.7 to 17. That would be a misinterpretation of the empirical data. So it's important that we understand the empirical data, and it's important that the empirical data is clearly defined. So as from that, we go into this particular technical bulletin reported 376. The points that Mr. Geiben has pointed out is that for a sensor network with a general configuration, what we're seeing, and the significance of the 2 sensor and the 4 sensor, is the 2 sensor is when you combine multiple technologies, you can get away with less sensors and the same information. It would stand to reason that immediately you're in a position where you are able to gather more information when you have the same number of sensors in both. Now, this 76% detection efficiency for the time of arrival system compared to 96.5% for the combined technologies is a concern when we talk about systems that are time of arrival only, and we have got equal number of sensors and the numbers. So the information here is not biased. It is an accumulated C-grade project and detailed analysis, and the documentation, TB376, is freely available to be verified and checked. What this data says is that if you have a shorter distance between your sensors, your detection efficiency will go up. Now, with the combined technologies, 96.5% to 97%, it's not huge. However, with the time of arrival, when you have your sensors closer together, you go from 76% to 80%. Well, that is considerable. The opposite is a concern when we go from 150 kilometers, which is the middle row, we go to the 300 kilometers. And what we see now is the combined technologies goes from 96.5%, goes down to 89.5%. So we've lost 7% detection efficiency. If we do the same thing with time of arrival, we go down from 76% down to 56%, which is enormous, 20%. We effectively we're kind of capping, we're saying we're detecting only half of the lightning activity out there. So what this tells us is that there is a direct relation between the positioning of our sensors before we even start talking about the overall networks. And this leads us directly to an understanding that when you're using combined technologies, you should be able to get by with at least half the number of sensors in the combined technologies network as opposed to the time of arrival only. The time of arrival was the original advanced systems that we had in South Africa. When I put my slides together, I pushed a whole lot in because it was so excellent. I need to find that I was talking too much. The Technical Bulletin 376 pulls in this scenario of having for Europe, and this is what Mr. Geiben was talking about, is the exterior, the whole of Europe is reporting lightning activity in region A and region B. Region A is the sensors only within Austria, and then region B is an internal area within region B. So I want to just wrap up with this slide. And what this slide says is, and I'm just going to go to the bottom window, which is for region B, is that when you have 3 sensors with combined technologies and you have 8 sensors with the time of arrival and a limited analysis, you actually end up with the same performance. So what the table at the 7.2 points out is that if you have a time of arrival network only, you can expect to, in this case, have more than double the number of sensors for a time of arrival network than you would require for a combined technologies network. And it's for this reason that we in South Africa went for the combined technologies solution. So as we kind of just step back from this now, that the importance of having correct or accurate lightning location systems for our ground place density maps translates to our risk, which is if we look at the second column, and I'll close on this, table 7.2. The second column, the green area, Euclid 100%, is the peak current reference measurement is 9.7 kiloamps. Unfortunately, the time of arrival overreads, and we end up with a 24% magnitude value greater kiloamps than what has actually occurred. What you'll see above, where we have got perimeter effects, that error can be up to 44%. So that's very significant in terms of our risks. I'm going to stop there and hand over to Andreas to wrap up.
Thank you, Richard. I appreciate that. Right, we have some questions here. I just quickly need to pull them up. We do aim to finish in the next few minutes. So so if I can please ask the answers to be as succinct as possible, please. The first question is for Dr. Hunt. So is it true or not true that lightning does strike the same place twice? So I think the question is it true or not true?
It definitely is true. Lightning can very much strike the same place twice. That's the idea that it doesn't is a myth. It definitely does.
I suppose the question is, are you talking about striking or flashing? But I think we understand the question and answer. Okay, then the next one is a comment, but I suppose it kind of fits in with another question. So the comment is to the weather service. It's addressed to Rydal, but maybe addressed also to Morne. And that's regarding shrinking revenues. The weather service can look into selling their services to utilities like Rand Water, who could be keen to track storms and rain patterns around their catchment areas. And then the question is what or how can one justify from a business perspective for increasing the detection efficiency? In other words, installing more sensors in areas with low lightning activity, such as the Northern Cape that was mentioned in, I think it was Morne's presentation. So, Rydal, Morne, feel free to take that question or that comment, please.
Okay, I guess, Morne, are you taking it?
No, you can go, Rydal.
I think in the first case, the water research, probably we need to look into that and get them probably on board as one of the potential clients to the South African Weather Service for lightning data. In respect of optimizing the network, I think there is a lot of input that was given even by Dr. Johan to indicate exactly what you could be using and what information you could be using to substantiate your request for actually optimizing a network or increasing the performance of that network. Thank you.
Yeah,
If I could jump in there briefly, Andreas. Oh, sorry, let Morne go.
Yeah, just to also further elaborate on the area like the Northern Cape, for example. So this is an area in our country where we don't have weather radar. And even though there's not a lot of thunderstorms there, they still do occur. So a lightning detection network is an excellent supplementation to our weather radar network. So that's one motivation that we can include.
I think if I may.
Okay.
So one of the issues to consider, given the tables that I just presented now, is the shorter your baselines, the immediate two things happen. Your detection efficiency increases, and your voltage, or your electric field measurements improve, so your accuracies of kiloamps increases. However, there is an immediate cost involved. So it's not a case of further research to come up with better technologies. It's a simple redundancy equation. If we want to improve our detection efficiencies so that we can start talking about detection efficiencies of 100%, it's entirely achievable. However, we must reduce the baseline distances, and the moment we reduce the baseline distances, it means the number of sensors in the network must increase. Now, at between $70,000 and $80,000 per unit, the understanding must be, how desperately do we need it? Is it a nice to have? Is it a luxury item? Or is there actually a cost impact in the industry? And this kind of brings us back to the essence of the risk management, is what is the need and the risk impact in South Africa that we should want to go to 100% detection efficiency. You know, when one looks at Florida in the USA, a time of arrival system that's covering that area, which is 132,000 square kilometers, is nearly 80 sensors. That's 80. Now, Florida is 132,000 square kilometers. South Africa is 1.2 million square kilometers, about a 1 to 8. So if we were using that time of arrival technology in South Africa, to get close to the 100%, we would need 80 sensors multiplied by 4. Let's do the maths. It's a horrendous amount, considering that currently the Sldn is 25 sensors. I think the Earth Networks, from Colin mentioned, is 24 sensors. So the information we've covered today says there are good networks and there are good networks. The technologies determines how many sensors you need. And it's not a case of we need more research. What we need is to ensure that we've got the right number of sensors. And the right number of sensors costs money. It means that we in the lightning industry, science community, and within the lightning protection industry, is we need to get our act together to quantify these things for the stakeholders. You know, kind of going back to the ISO SANS 31000 risk management, it's very clear that there's no rocket science required. We just got to apply discipline. What Rydal and Mornay was talking about in terms of our working together is we need to get that together, put the RANds value to it, and then have a strategy of how long it's going to take us to get to 100% detection efficiency. And when we then say, well, we don't need 100% detection efficiency, if we say that, we put it in writing so that we don't try and strive for it, we don't try and outmarket each other from a commercial perspective.
Thanks, Richard.
Hugh?
Yeah. Yeah, Hugh.
Good. You can go to the next one.
Okay. Then just one final question for Richard. Coming from the fact that you had that video up at the beginning from basically a member of the public, do you see a space for that type of, in inverted commas, citizen science in lightning protection in this country?
What is very interesting is that we have the predicament, if I can call it that we don't know what we don't know. We can't say what we can't see unless we've got a tool to see it. So in my years in Eskom, the thing that I really appreciated is that you got a let's say distribution network, 9 provinces, hundreds of thousands of kilometers, and every one of those provinces there's an operational performance that when a network trips, there's an event happening and we can link it. The more feedback that is brought back to the service providers of the lightning detection network, the lightning location system, the better the understanding what questions to ask. So, if we talk about a nuclear power station, and if it's, depending on where it's positioned, Cape Town lightning density is very low, but if we have these hospital that has life support systems, positioning additional sensors allows us to improve the performance in localized areas. This is done in the US with NASA, with the space launching the space goodies. And in Europe, a couple of areas where they need to improve, need better information, is just a higher density of sensors. So the benefit of information like what we've seen with that public submission is we start seeing more, and from the South African Institute of Electrical Engineers Lightning Chapter perspective of wanting a drive to push lightning safety and lightning awareness and what to do in the right place. Our children in schools, our teachers, our parents, the information that's being shared, the more feedback we get, the better we can be positioned to honestly find the best solutions for our people. So absolutely, we need to keep an open mind, but of course there's an aspect that we need to facilitate, is how to receive that information in a way that we can separate the verified information versus the subjective information. And when one sees lightning, the intense light that gets generated, you think the lightning is just right next to you, and the enormous bang of the sound, you start thinking half my own house has been blasted away. When you look at the data, actually it occurred maybe a kilometer away. So there is that aspect that requires filtering. But our drive to increase lightning safety and awareness, our schools in the rural areas, the questions about houses that people that don't have the ability to implement their own lightning protection, what mechanisms are we putting in place to assist them, from a governance facilitation, funding, and you asked for short answers. I'm not doing very well.
Thank you, Richard. That's all good. Right, that was all the questions. I would then just like to give a big thank you to everybody involved tonight. Firstly, the 4 presenters, especially, as I said at the beginning, Richard, who kind of pulled everything together and did most of the organization. I just got the very relatively easy job of just hosting this evening. I would also like to thank Minx, who did the technical organizing and who really kept us on track tonight, and who will then also be doing the admin with respect to the CPD application. And finally, thank you to everybody who attended. We had more than, I think, certainly way more than 30 people who attended. It obviously fluctuated a little bit. I hope you found this useful, found it interesting. For those of you who are not members of the Lightning Chapter, please do join. If you need to know how to join, just send an email to the Institute and they will pass that on to us. You do not need to be a member of the Institute to be a member of the chapter, and it's also free of charge. So if you are interested, if this is whetted your appetite, please do join. You also don't need to be an engineer. It's really open to anyone. Then please give us a shout. That is all I need to say. So except just to wish everybody a good evening and a safe evening, and stay safe and healthy. Thank you and good evening.
Okay, good evening. Thanks, Andreas.
Thank you.